Let's suppose that a clutter of friends want to eat sushi. And so you go to your beloved cozy store and ask, "Hey beloved friends, which sushi do you want?" And this cute question followed by a response is precisely the essence of a function. But on the other hand, how is this math? This is just an analogy, right? Surely there can't be mathematical objects called sushi, right? Surely I'm just trying to capture your attention. On the other hand, it's not an analogy. Math is not about numbers, and I not only mean that in its literal or metaphorical sense. Obviously, math is not metaphorically about numbers, and what it literally is, you will find out in this chapter. So the sushi scenario is supposedly a real piece of math, but how could it be related to algebra? Mathematicians determined that an imaginary world of equations is connected to people asking for sushi. My art that I want to share today illustrates that these two concepts are related by introducing the fundamental foundation of math. Numbers do not construct numbers. Instead, numbers have definition by the abstract yet beautiful theory of sets. When someone departed from saying 5 faces, 5 sushi, and let 5 be a number on its own, math was invented. Then people developed ways to manipulate numbers. It continued for millennia with the invention of ideas like fractions, the number 0, and negative numbers. At a certain point, people are using letters to symbolize numbers. However, by the late 19th century, creative mathematician Georg Cantor discovered an even more foundational idea than counting, which is the idea of collections. Once you have a collection of things, or as they call it, elements, you have a set. That is set theory. Sets are denoted by curly braces, and the collection of things go inside them. They are easily manipulable like numbers. We will bite the two most important things you can do to sets in this chapter: counting and pairing. Anything can be in a set. This includes numbers, people, countries, and even sets themselves. A slight caveat though, sets are special collections. You can change the order of a set or add the same thing in a set any number of times and still call that the same equivalent set. And of course, there are motivations behind this, like anything else. It turned out to be useful that we define sets this way, which you may discover why later in this chapter. Going back to our cozy sushi store, we see that there are two sets: your friends that are asking for a certain type of sushi, and the distinct flavors of sushi available. Here we see the idea of pairing sets. The friends kindly ask you for a flavor of the sushi, which is a pair of two elements taken from the two sets. And that is precisely the nature of a function. A function is defined as a pairing of an element, which remember is just one of the things in a set, with another element in another set. But it's not actually an honest pairing, it's more like a mapping. Let's give our sets names. The friends I will call A and the sushi I will call B. Then the function is not necessarily a pairing between A and B. It's either that the elements in A get paired to the elements in B, or the elements in B get paired to A. In other words, the function goes in one way, sometimes the other way, and sometimes both ways. And you see why it's preferable to define function as a one-way pairing rather than defining them as a two-way pairing. If it was a two-way pairing, then there must be the same amount of elements in one set as in the other set. But here, the set B has more elements than A. So functions go in one direction, and here the function travels from A to B. Our definition so far is as follows. A function is a one-way pairing from a set to another set. As you've probably heard before, we call a set that is going to pair with something else the domain of a function. And just for our sake here, let's give our sets names. Just like variables, it can be denoted by any letter, x and y, and an m, your choice. Now, we would expect that if A is the domain, then B is the range. But that's not the case. The range is instead defined to be the set of elements in B that A pairs with. So if every element in B did indeed get paired up with an element from A, then the range would be B. But if there was a leftover in B that was not attached by anything from A, then the range would only be part of B. To entertain your curiosity, B is not the range but is instead called a codomain. In other words, A is the domain, B is the codomain, but the range of values that the elements in A are paired with in B is called the range. our definition is still lacking. You will see that you will encounter functions very, very often in algebra, but you wouldn't want to write a function from x to y just to denote a function every time. So we give it notation. Usually, they are denoted by the letter f for function. However, functions have the capability to be denoted by any letter, like variables, but you can also denote them by words. Mathematicians decided that the best way to express that f is a function from a domain A to a codomain B is written as f colon A arrow B. This is read as f is a function from A to B. It simply means that we have a function called f, which is a one-way pairing from A to B. And that completes our definition. I am fond of our definition since it logically means the same thing as how any textbook would define it, while maintaining an intuitive sense and elegance. But if you have not realized that, when I say one-way pairing, I mean that every element in A must get paired to a single, not two nor zero elements in B. That's another aspect of good definitions. The best definitions are rigorous and unambiguous, or in other words, have no room for different interpretations. I will argue that our definition is rigorous, but it depends on your definition of a one-side pairing. Another rigorous way that Wikipedia defines it is that a function from a set x to a set y assigns to each element of x to exactly one element of y. Lovely! That is set theory and how it's useful in a nutshell. It accepts the idea of numbers, but it also opens a novel and exciting world of imagination. You can now imagine a universe where cozy sushi stores are mathematical. Sets are even more foundational than counting. But why does it matter that something is more foundational than the other? How are sets foundational anyway? On the other hand, why do physicists yearn to unveil the fundamental laws of the universe? Why do they care that an atom is made of neutrons and care that a neutron is made of quarks? If numbers were the atoms of the universe, then sets are the neutrons, protons, and electrons of the universe. That's exactly what it means. Sets define everything in a mathematical cosmos. The first pages of an advanced textbook are always filled with definitions and theorems that are oftentimes described by set theory. We care that sets are foundational because a goal of mathematics is to make as few assumptions as possible, known to be axioms. Then we construct quality definitions that we think to be useful. After we have definitions and axioms, we have set the building ready for construction. Definitions provide the Legos to work with, and axioms provide the truths of what we are allowed to do with those Legos. Combining the Legos, we get theorems. Theorems are facts or theories that have been proven to be true, but unlike theories, they absolutely cannot be wrong unless you change the axioms or definitions around. It is only then that you reach the domain of what middle and high schools teach, which is to apply these theorems. When you say that x equals 1, then x plus 1 equals 2, you are really just applying a theorem that asserts if x equals a, then x plus any number equals a plus any numbers. And it's truly unfortunate that we will never learn how to properly prove theorems in school. This example theorem, as you will see later, is trivial to prove with the help of functions. Mathematicians solve difficult problems too, but most of their time is actually spent on constructing proofs of certain theorems. In essence, we don't want to make an axiom that states the existence of numbers when we already have axioms that account for sets, so we define numbers using only sets. And yes, technically speaking, this applies to sushi as well. Sushi is not a part of math unless we create definitions for sushi. To avoid making these axioms, we want to make definitions for numbers instead. How should we start? I think either 0 or 1 would be the best thing to start with, since those are the simplest numbers out there. Let's go with 0. Maybe you would think of defining 0 to be the set that contains 0. But how would you use 0 if we haven't defined 0 already? And what even is 0? 0 means 0. In the real world, it would mean that there are 0 things, whatever those things are. But wait, what if we use that as our definition? It turns out that mathematicians agree. They decided that the best definition for 0 is the empty set, the set that has no things in it. One similarity is the set that has one thing in it. But we've only defined one thing so far, which is 0. So we just use that one thing we've defined, and that's the definition of 1. 2 is the set that has 2 elements, specifically the 2 things that we have defined so far, 0 and 1. This is how every integer greater or equal to 0 is defined. Combining these numbers, we can construct a set. This is a set of natural numbers, and since it's so common, there's a special symbol. Whenever you see this blackboard bolded n, it is just a set of all positive integers. Obviously, that's not enough for algebra. How are we going to use negatives, fractions? So we have to make those too, although I will have to skip the definitions. The set of all integers, which includes the negatives, is denoted by z. Then we have the set of all rational numbers, q, which in essence is every fraction that you can make with integers. Finally, the set of all real numbers, r, is the set of rational numbers, but with the addition of irrational numbers, that is, numbers that cannot be expressed as a fraction of 2 integers. For example, the square root of 2. Root 2, as one might not expect, is not a rational number. The combination of every number that is a rational or irrational number leads to every number that is inside negative and positive infinity, which are the real numbers. Finally, you see how sushi and algebra are related. One can construct a function that pairs the real numbers with the real numbers. Sadly, all if not most of the functions you see in algebra are concerned only with the set of all real numbers. We, unfortunately, will not be using the f:\arrow notation for functions much, since it will be implied that the function is a mapping from the real numbers to the real numbers. If you ever see a function, you can and should assume that it is a function that maps the reals onto the reals, unless specified otherwise. That's okay though, there's still plenty of interest in the real numbers that I want to share with you. Now I want to introduce the other way of thinking about functions. We've defined functions as a one-way pairing from a set to another set. That by itself is useful. For example, if you know that there exists a two-way pairing, then you know that the two sets have the same amount of elements in them. That's actually a tool used to prove the unobvious fact that there are different kinds of infinities. But before the 19th century, functions symbolized something different. Interestingly, addition and multiplication by themselves are function. But does that make sense to you? In addition, we don't take a single value, we take two. And then those two values are paired to another value. To solve this problem, we treat two values as a single input. We are going to use the ordered pair notation that we know. Now this satisfies our definition of a function in that every element in the domain gets paired to not 0 nor 2, but one element in the codomain. And our domain is not the real numbers, it's a special set which is fancifully called the Cartesian product of R cross R. But don't worry about notation. This is merely a set that has ordered pairs as its elements inside. And since this ordered pair gets mapped to some real number, the codomain is the set of all real numbers. But just saying that isn't really too practical, is it? We already know that addition is a pairing of an ordered pair to another value. This is why functions have historically been treated as machines rather than pairings. Machines, like your calculator, will tell you what 1 plus 1 is. This distinct, or rather seemingly distinct, idea is extremely convenient. It not only tells us that there is a pairing from one set to another, but it tells us exactly which pairings occur. Let us take a machine that takes in a number, but then produces the square of the number for us. Then this machine is also a pairing between two sets, the real numbers to the real numbers. 2 is paired to 4, 3 is paired to 9, and 4 is paired to 16. Because every element gets paired to a single element, it is a function. Now I'm going to call this function square since we are allowed to denote functions by words. But here we see an inconvenience. You and I would not want to write 2 is paired to 4, right? So again, we define notation. It can be anything, but the mathematician Leonhard Euler decided that we should denote it like f parentheses, or rather in our case, square parentheses because that's the name of our function. Whatever goes in these parentheses is the name you want it to be paired. And whatever this entire expression, combining the two and the name of the function, is what it gets paired to. So 2 gets paired to 4, Therefore, we put a 2 in the parentheses and a 4 to the equal sign. This is read as square root of 2 equals 4, square root of 3 equals 9, and square root of 4 equals 16. This is the first of many instances in math where notation may get ambiguous. Notice what happens when we change the function name to f. According to what we previously learned, you would think that this is just 2 times f, but it's not. It's read as f of 2. To distinguish between f times 2 and f of 2, you need to use context clues. But usually, if it's a letter or word followed by parentheses, it is a statement that tells you what the elements of the domain get paired with in the codomain. And of course, we wouldn't want to list what every element is paired with since there are infinitely many elements in the set of real numbers. Even between 0 and 1, there are an infinite number of elements, but we are skipping those because the naturals are nice to work with. Since we are dealing with infinite potential values of a thing that something can take on, we should use a variable to account for that. And since we know that every input turns into the input squared, we can write that our variable x with the function is equal to x squared. Here, square root of x equals x squared is our explicit definition of the function square. In high school math courses, although not nearly as much after that, functions are almost always given an explicit definition. The explicit definition tells you what each element in the domain gets paired with. As a test, if I had a function g with the explicit definition, g of t equals t cubed minus 5t, what value does 2 pair with? It would be whatever 2 cubed minus 5 times 2 is, right? You simply have to plug in 2 for every t, just like you would in an equation. The explicit definition tells us that it's a function that takes in some number, t, and turns it into, or maybe pairs it to a number that is that number cubed minus 5 times that number. So let's go back to our addition function. Our explicit definition is f of x comma y equals x plus y. If you graph these functions, we have a pleasant 3-dimensional graph due to there being 2 variables, and an additional paired value that acts as another variable. A dimension in the mathematical universe is like the number of ways you are changing. We can think of the function as taking in x and y as inputs, which then pairs an output into the z-axis. The elements in the domain are inputs, while the elements in the range are outputs. And since it's pleasant to glance at, here's what the multiplication function looks like. The explicit definition is f of x comma y equals x times y. Since the domain is every ordered pair of real numbers, every possible combination of real numbers is in the x and y. However, since z is what x and y get paired to, there's only a single z for every combination of x and y. Algebra is the study of deriving truths from relation, and functions are a special type of relation. We have seen the linear equation y equals mx plus v. Most teachers will call these functions. For all x, the x is paired to exactly one y, not 2 or 0, and that satisfies the key defining property of a function. In a way, it is a function since if you let f of x equal y, you can rewrite it as f of x equals mx plus b. If you don't like to see y in a function, you can always let y equal f of x and vice versa. In graphing questions, if you see a problem that asks to graph f of x equals whatever, then you should treat f of x as y. In a way, you can think of the output variable as an abstraction of f of x. Teachers quintessentially introduce functions as gadgets that take an input and produce an output, and it's fair to say that it only makes sense for every input to produce a single output. To take this analogy further, think of a game. In Genshin Impact, you can attack enemies, and there are multiple inputs at play. How many attack points do you have? How many defense points does your enemy have? The damage points, P, an attack does can be modeled by a function with 2 inputs. Of course, these 2 inputs are actually just one single ordered pair, but we can still say that it is a function that takes 2 inputs. This is a good example where a function is not explicitly defined by its inputs. Here, the function d is just here to say, hi, I'm a machine that takes in a and d. And the p is there to show that the points of damage done is equal to the value that a and d are paired to. It doesn't have to be there, like how one doesn't have to explicitly state that f of x equals y. D is a function because every input pairs to, or in this case the better word would be that like a machine, it produces a single damage point. And we don't care about RNG since this is a model of what actually happens. So for this model's sake, the same inputs will always result in the same output. In algebra, you will and are already learning about polynomial functions. Linear functions are a type of polynomial. But then you will also learn about rational functions, functions that are a fraction of two polynomials. But that's not everything you learn in arithmetic. You also learn about taking square or cube roots. Hence, radical functions are also taught. We also have the notion of exponentiation, so we will learn about exponential functions as well. And finally, my favorite, logarithmic functions, a totally novel method of manipulating a number. As you can plainly see, functions are at least 90% of algebra. But what's the missing 10%? Relations that are not functions. Take the relation y squared equals x. And here I should mention that the y is being treated as the output. If we input some 1 for x, y is 1, but it's also negative 1. Negative 1 squared is 1. There's more than one output for an input, and hence it is not a function. Sometimes we say that you can use a quote, vertical line test to test whether a plotted equation on a graph is a function or not. If you can find a single vertical line that crosses more than a single point, then that equation is not a function. Because if 2 points cross a vertical line, that means there are 2 y's for 1 x. That's not good. There has to be exactly 1 y for each x. But this is all under the fair assumption that x is the input here, while y is the output. If y was the input, then we would rotate the equation by 90 degrees, and the equation will be a function. Here's a final addition to our function notation. Say we have a function f of x, which is defined by x squared. This is the graph of that function, and of course it looks like the function y equals x squared. If we change the function f of x into f of x plus 1, what would happen? Well, f of x plus 1 is asking what x plus 1 will get paired to. And x will get paired to an x squared. So it would make sense that if you change the input by 1, it changes the x in the definition by 1 along with it. We are altering what the input is, and this change affects the definition in the same way. And consequently, this shifts the new graph horizontally by -1. I know that sounds counterintuitive, but I promise that it will make sense in chapter 2.3 with something called function transformations. To generalize all of this, if you have any function g, and change the input by something, then every instance of that input changes to whatever the new input changed to. This leads me to the idea of function compositions. It's the idea that a function is inside a function. In Genshin Impact, it happens because the input itself is a function. The attack points are defined by the artifacts, level, and weapon that this player has. It has 3 inputs, or an ordered triplet if you will. And the defense points of the enemy, well, that's a bit more complicated, so we can leave that as a variable that has no underlying relations or functions. Actually, even our other example are function compositions if you think of x plus 1 and 2x minus 5 by itself as a function. And of course, if you compose a function, that means you can change either every input to the name of that function, in this case h of x or j of x, or the thing that it is defined by. Now, this is probably the most useful and applied theorem in algebra, which is that if a equals b, then it is also true that f of a equals f of b. It's trivial to prove. If one element is paired to another, then an equal element would be paired to the same thing, right? If that makes you uncomfortable, first see that f of a is clearly equal to f of a, and then simply replace the a in f of a with b, since that is equal to a. Then we get that f of a is equal to f of b. You've been using this theorem since you started algebra. We know that if a equals b, then a plus x equals b plus x for any a, b, or x. But this is actually an application of this theorem. If we let f of x equals x plus 1, then since we know that f of a equals f of b, we can say that a plus 1 equals b plus 1. And the 1 can be any arbitrary value. If we say that a plus 2 equals b plus 2, then we can simply let f of x equals x plus 2 as our justification. That is the reason why we can add both sides of an equation. So simple, right? This also explains why you are allowed to subtract from both sides, or why you are allowed to square or cube both sides. But what about square roots? How come when x squared equals 4, x equals 2, and negative 2? Can't we let f of x equals the square root of x? I would like to explore this idea in chapter 2.2, where we will explore the two-way pairings I mentioned, which are connected to the idea of inverse functions. But just looking at this graph, can you see why? Can you see the difference between f of x and the inverse of f of x? And how would that apply to the reason why we can't take the square root of both sides when you treat the square root as a function?